Humanity has sent rovers to Mars, probed the outer edges of the solar system, and built computers that process billions of calculations per second. Yet, every time you board a commercial flight, you are stepping into a technological time capsule. At 36,000 feet, modern passenger jets are bound to a strict universal speed limit, roughly 950 kilometers per hour. For over half a century, commercial flights haven't gotten a single kilometer faster. It is not because we lack the engines, or the engineering, or the ambition. It is because at that exact speed, the invisible air around the plane transforms from a lifting fluid into a concrete wall. What exactly happens to a machine that pushes beyond this limit? And why did the aviation industry silently decide that breaking this invisible barrier is a catastrophic risk we can no longer afford? To understand why we are trapped at this speed, we first have to understand why we fly so high. The story of modern aviation's limits begins with a mystery over the Mediterranean Sea. On January 10, 1954, a British de Havilland Comet took off from Rome. It was the world's first commercial jetliner. It flew twice as fast and twice as high as the propeller planes that came before it. The passengers inside enjoyed unprecedented silence and a smooth ride above the weather. But 20 minutes after takeoff, communication abruptly stopped. Witnesses on the ground saw a flash in the sky, followed by debris raining down into the water. To solve the mystery of why this marvel of engineering fell out of the sky, investigators built a massive water tank, submerged an entire fuselage, and simulated the pressurization of flight. After 3,000 cycles, the metal tore open. The origin of the failure was a tiny microscopic crack at the corner of a square window. Engineers realized that at 11,000 meters, the aircraft acts like a balloon. The air outside is incredibly thin, lacking the oxygen required for human survival, so the cabin must be heavily pressurized from the inside. With every takeoff and landing, the metal fuselage expands and contracts. The tension concentrated at the sharp corners of the square windows until the metal snapped like an over-tightened guitar string. This tragic lesson forced a total redesign of aircraft, giving us the round windows we see today. But more importantly, it permanently established the ultimate cruising altitude for humanity, 11,000 meters, or roughly 36,000 feet. This is the sweet spot. The air here is thin enough to eliminate massive aerodynamic drag, allowing planes to glide efficiently, yet dense enough to provide the lift needed to keep hundreds of tons of metal airborne. This delicate balance of atmospheric density and material strength is what locked in our speed. At this specific altitude, 950 kilometers per hour is the point of maximum efficiency. But what happens if a pilot decides to ignore this equilibrium? What if they push the throttles forward and demand more speed from the engines? The answer lies in a terrifying aerodynamic trap. Even if the engines have the thrust, and even if the fuselage can hold the pressure, the aircraft will suddenly stop obeying the pilot's commands. It will become an unguided missile. We tend to think of air as empty space. But at high speeds, air is a physical substance with its own brutal laws. To understand the 950 km/h limit, imagine moving your hand through a pool of water. Move it slowly, and the water parts easily, flowing smoothly around your fingers. Move it violently, and the water resists, feeling almost solid. The wings of an airplane rely on this smooth flow of air to generate lift. The top of an airplane wing is curved, while the bottom is relatively flat. As the plane moves forward, the air traveling over the top curved surface has to cover a longer distance in the same amount of time, forcing it to accelerate. This means the air flowing over the wing is moving significantly faster than the airplane itself. And this creates a hidden danger. When a commercial airliner reaches 950 kilometers per hour, it is still flying below the speed of sound. But because the air accelerates over the curve of the wing, the localized airflow right above the passengers' heads actually breaches the supersonic threshold. At this exact moment, the physics of the air fundamentally change. The smooth, lifting fluid collapses. Invisible, violent shockwaves form on the surface of the wing. These shockwaves act like a physical barrier, separating the airflow from the metal. The air no longer glides, it hammers against the structure. In the 1940s, test pilots attempting to push early jet engines to their limits encountered this terrifying phenomenon without understanding it. As they approached the speed of sound, their aircraft would suddenly violently shake. When the pilots pulled back on the controls to lift the nose and slow down, the plane would do the exact opposite. It would pitch downward, diving toward the earth. They called it control reversal. The shock waves on the wings completely disrupted the air hitting the elevators and ailerons, the moving parts that steer the plane. The controls became completely useless. The air was pressing down on the machine with such chaotic force that the laws of aerodynamics seemed to invert. Many test pilots did not survive these early encounters. Engineers eventually learned to sweep the wings backward to delay the onset of these supersonic shock waves, a design visible on every modern airliner today. But swept wings only delay the inevitable. 950 kilometers per hour remains the critical boundary. Push past it, and the air transforms into a chaotic, destructive force. This boundary creates a perilous balancing act for modern pilots, an invisible tightrope drawn across the sky. In aviation, this narrow margin of survival is known by a dark and unforgiving name, the Coffin Corner. Imagine walking on a narrow suspension bridge over a bottomless canyon. If you step too far to the left, you fall. If you step too far to the right, you fall. At 36,000 feet, commercial airplanes are walking this exact bridge. Because the air is so thin at this altitude, the airplane must maintain a very high speed just to generate enough lift to stay airborne. If the plane slows down even slightly, the thin air can no longer support its massive weight. The wings lose their grip on the atmosphere, and the plane stalls, dropping like a stone. But if the pilot tries to fly faster to avoid the stall, they immediately run into the invisible wall of the sound barrier. The supersonic shock waves form on the wings, the violent vibrations begin, and the aircraft loses all flight control. The higher the plane climbs, the thinner the air gets. The stall speed increases, while the speed of sound decreases due to the extreme cold. As the plane climbs higher, the gap between going too slow and going too fast shrinks. At peak altitudes, the safe operating window can narrow to just a few dozen kilometers per hour. There is absolutely no room for error. This is the Coffin Corner. Step out of bounds in either direction, and the machine falls out of the sky. On the night of June 1, 2009, the reality of this invisible trap was demonstrated with devastating consequences. Air France Flight 447 was cruising through a storm system over the dark Atlantic Ocean. Deep in the night, ice crystals began to form on the pitot tubes, the external sensors that tell the airplane's computers how fast it is moving. Blinded by the ice, the flight computers instantly lost their speed data. The autopilot, designed to keep the plane perfectly balanced on the tightrope, disengaged, handing manual control back to the startled pilots. In the dark cockpit, chaos erupted. The instruments began feeding contradictory numbers. Alarms blared, warning of impossible conditions. Without reliable speed data, the pilots were flying blind inside the Coffin Corner. Unable to find the narrow margin of safety, the aircraft stalled. The sophisticated, state-of-the-art airliner plummeted from the sky, crashing into the ocean in just 3.5 minutes. To prevent this from ever happening again, modern aviation relies on digital locks. Today's flight computers act as invisible guardians. Even if a pilot intentionally tries to push the throttles to the maximum to break the speed limit, the software simply ignores the command. The machine knows what the human ego might forget. Beyond 950 kilometers per hour, the sky is no longer a pathway. It is a trap. But what if we refuse to accept the trap? What if we redesign the entire aircraft from the ground up? Ignoring efficiency and focusing purely on overpowering the physics. We have done it before. And it revealed an entirely new layer of danger. When you push a machine past the speed of sound, you don't just fight air pressure. You fight thermal destruction. You hit the heat barrier. The legendary Concorde was a marvel of human defiance. It routinely carried passengers across the Atlantic Ocean at over 2,000 kilometers per hour, faster than a rifle bullet. But flying at Mach 2 required a terrifying compromise with nature. At speeds beyond 1,000 kilometers per hour, the air ceases to act like a gas and begins to act like sandpaper. The sheer friction of the air molecules slamming into the nose and leading edges of the wings generates immense thermal energy. During a routine flight, the friction heated the nose of the Concorde to a scorching 127 degrees Celsius. The heat was so intense that the physical structure of the aircraft fundamentally changed mid-flight. Standard aviation aluminum begins to soften and lose its structural integrity under such extreme temperatures. If a normal Boeing or Airbus attempted these speeds, their fuselages would become as pliable as a plastic bottle filled with boiling water. To survive the heat barrier, the Concorde required specialized alloys and incredibly complex engineering. But even with these advanced materials, physics took its toll. As the metal heated up, it expanded. During a transatlantic crossing, the fuselage of the Concorde literally stretched. The entire airplane grew longer by up to 30 centimeters. This thermal expansion was so severe that a visible gap would open up in the cockpit, right between the flight engineer's console and the rear bulkhead. The gap was wide enough for a crew member to slide their entire hand inside. Upon landing, as the metal cooled and contracted, the gap would tightly close. Building a plane that can survive melting its own skin is staggeringly expensive. It requires titanium, ultra-high-strength steel, and massive cooling systems intricately woven through the airframe. These materials are incredibly heavy, making the aircraft difficult to build, expensive to maintain, and highly inefficient to fly. Even if we possess the engines capable of extreme thrust, the fundamental molecular bonds of the metals we use dictate our boundaries. We cannot mass-produce cheap, lightweight planes that fly at supersonic speeds. The heat barrier ensures that going fast will always be an engineering nightmare. Yet, even if we accept the astronomical costs, even if we build an indestructible aircraft of titanium that can withstand the melting heat and the chaotic shockwaves, we run into a barrier that has nothing to do with aerodynamics. We run into human civilization. Speed creates a phenomenon that is impossible to hide and impossible to ignore. When an aircraft surpasses the speed of sound, it outruns the very noise its engines create. The air ahead of the plane cannot move out of the way fast enough. The pressure waves compress, stack up, and merge into a massive, invisible wall of highly pressurized air. This is the shock wave, and it trails behind the aircraft in a massive cone, stretching all the way down to the surface of the Earth. When the edge of this cone sweeps across the ground, the sudden change in air pressure is perceived by the human ear not as a mechanical roar, but as a violent, explosive detonation. The sonic boom. In the early 1970s, as the United States military and aerospace industries tested supersonic flight, the public experienced the terrifying reality of the sonic boom. It was not a brief inconvenience. Imagine sitting in your living room, and without warning, an explosion shatters the silence. Windows cracked. Plaster fell from ceilings. Valuables rattled off shelves. Parked cars on the street simultaneously triggered their alarms. People ran out of their homes in a panic, fearing a military attack or an earthquake. But it was just a plane passing miles overhead. What engineers failed to realize was that a sonic boom is not a single event that happens only when the plane breaks the sound barrier. It is a continuous carpet of destruction. As long as the plane is flying at supersonic speeds, it is dragging that explosive shockwave across every city, town, and farm beneath its flight path. The public outrage was unprecedented. The noise pollution was deemed a fundamental threat to the psychological well-being and structural safety of the population. The government faced an ultimatum: the progress of technology, or the peace of millions of citizens. In 1973, the United States, along with many other nations, instituted a strict legislative ban. Civil supersonic flight over land was outlawed. This single piece of legislation created a legal brick wall in the sky. It did not matter if engineers could build the perfect aircraft. It was illegal to use it to its full potential anywhere except over the empty oceans. Airlines quickly realized there was no profit in building a fleet of hyperfast jets that were legally forced to crawl at subsonic speeds for half their journey. Physics created the sonic boom, but the law finalized the speed limit. With supersonic flight banned over populated areas, aerospace engineers asked a new question. If we cannot break the sound barrier, can we get as uncomfortably close to it as possible? Can we push the limit to 99% of the speed of sound? In the early 2000s, the Boeing company attempted exactly this. They unveiled a highly ambitious project known as the Sonic Cruiser. It was a radical, futuristic aircraft designed to cruise at over 1,100 kilometers per hour, skirting the absolute ragged edge of the sound barrier without creating a sonic boom. Airlines were initially thrilled. The Sonic Cruiser promised to shave hours off transcontinental flights. It seemed like the first true leap in commercial aviation speed in decades. But behind closed doors, a brutal mathematical reality was taking shape. The problem was aerodynamic drag. At 950 kilometers per hour, a passenger jet already expends a massive amount of energy just pushing the air out of its way. But the drag equation is not linear. As you approach the speed of sound, the air resistance increases exponentially. When Boeing's engineers tried to squeeze just 150 extra kilometers per hour out of the design, the required thrust skyrocketed. The math was merciless. To save 1 hour of flight time, the Sonic Cruiser would need to burn 20% more fuel. This completely destroyed the economics of the airplane. More fuel meant the aircraft had to carry massive, heavy fuel tanks, which meant it required larger engines, which made the plane even heavier. leaving very little payload capacity for actual paying passengers. The ticket prices would have to be raised to astronomical levels just to break even. Simultaneously, airlines were analyzing the ground logistics. They realized that saving 45 minutes in the air was entirely meaningless if the passengers still had to spend 2 hours waiting in security lines, boarding terminals, and baggage claim carousels. The speed advantage in the sky evaporated on the ground. Faced with this insurmountable economic wall, Boeing abruptly canceled the Sonic Cruiser project in December 2002. All the research, the wind tunnel testing, the futuristic designs, they were quietly shelved. The industry made a definitive choice. They realized it is far more profitable to transport 300 people slowly and cheaply than to transport 50 people quickly and expensively. Instead of the Sonic Cruiser, Boeing built the 787 Dreamliner, an aircraft that flies at the exact same 950 kilometers per hour as the planes from the 1960s, but does so with incredible fuel efficiency. The aviation industry stopped fighting the atmosphere and surrendered to economics. To many, it seems as though commercial aviation has stalled, frozen in time while the rest of our technology races into the future. But the 950 km per hour limit is not a symbol of engineering failure. It is the exact opposite. It is humanity's greatest compromise. It is the precise intersection where the laws of thermodynamics, the chaos of fluid dynamics, the structural limits of metal, and the strict constraints of global economics all meet in perfect balance. We learn to build machines that do not vibrate apart in the Coffin Corner, do not melt from atmospheric friction, do not shatter the windows of the cities below, and allow a ticket to the other side of the planet to cost less than a smartphone. This invisible limit has formed the quiet, stable foundation of modern globalization. Yet, the nature of engineering is to constantly test the fences that confine us. Today, a new generation of aerospace designers is attempting to solve the sonic boom, engineering radical new hull shapes designed to muffle the explosive shockwave into a gentle, quiet thump. The barrier remains, absolute and unforgiving. But for the first time in 50 years, humanity is preparing to knock on the invisible wall once again. And when we finally break through, the sky will never sound the same.